The decades immediately following the detonation of the first atomic bombs were not a time of peace, but an era defined by a new, paralyzing form of global anxiety. The Cold War, that grim, protracted stare down between the capitalist West, led by NATO, and the communist East, dominated by the Soviet Union, became a technological arms race without precedent. Every year, laboratories and secret design bureaus across two continents strained to produce weapons that were faster, more powerful, and more capable of delivering destruction deep into the heart of the enemy. The strategic imperative was chillingly simple: strike fast, strike far, and strike without warning. The 1950s and 1960s were the golden age of missile development, a period that saw the rapid evolution from V-2 rocket lineage to the terrifying intercontinental ballistic missiles ICBMs. The world watched as names like Atlas, Titan, R-7 Semyorka, and Minuteman entered the global lexicon, each promising to reduce the travel time between launch and apocalypse. Military doctrine was rewritten daily, predicated on the concept of mutually assured destruction, MAD, a suicidal pact that held that no side would dare launch an attack because the retaliation would ensure the annihilation of both. Yet, even within this terrifying pantheon of doomsday machines, the massive rockets designed to carry multi-megaton warheads across oceans and continents, there was a specific design that stood apart. It was a weapon system developed with such radical, almost reckless, innovation that it genuinely terrified military planners on both sides of the Iron Curtain. It was not merely its destructive payload that caused such profound anxiety. Many missiles carried far larger warheads. The fear surrounding this particular missile stemmed from its unpredictability, its ability to circumvent established defense protocols, and its fundamental challenge to the stable, if terrifying, calculus of MAD. This was a weapon that pushed beyond the existing definition of a strategic missile, promising operational advantages that would destabilize the entire nuclear balance. Hypersonic velocity. While other missiles were fast, this design promised speeds that would render current detection and interception technologies utterly obsolete. It was designed to transition from launch to target in a timeframe that offered the enemy little to no reaction window. Near unstoppable maneuverability. Unlike the predictable, parabolic trajectory of standard ballistic missiles, this design incorporated radical aerodynamic controls that allowed it to shift course in flight, making final interception a near impossible dream. It was a guided phantom, an aerial ghost that defied tracking radar. The psychological edge. Its very existence threatened to collapse the crucial time margins required for political consultation and command and control decisions. It could force a nation to choose between a potentially false alarm and immediate, full-scale nuclear retaliation. The small, ultra-secret teams of physicists, propulsion engineers, and rocketry specialists who labored over this prototype, working in windowless bunkers and camouflaged test sites, grew to harbor a chilling sense of unease. They were creating something of undeniable genius, yet they privately doubted whether it should exist. The complexity and operational profile of the missile made it too close to a first strike weapon, a device so effective at decapitating an enemy's command structure that it made preemptive conflict far more tempting, and therefore, far more likely. This missile promised a power beyond anything deployed at the time, not necessarily in raw yield, but in its ability to guarantee target delivery. It represented the ultimate marriage of propulsion technology and guidance control, a technological peak that risked turning the Cold War from a stalemate into a desperate scramble for the trigger. And yet, despite the billions poured into its development, despite the strategic revolution it promised, and despite the profound psychological impact it had on both East and West intelligence, it never reached the front line. It never saw service in the hardened silos of the USSR or on the mobile launchers of NATO. The reasons why: the complex interplay of politics, technological hubris, and the sheer, impractical expense of perfection, are a story that has been deliberately buried under layers of secrecy ever since. Its legend lives on only in the heavily redacted pages of intelligence reports and the memories of the few surviving individuals who knew its true name and its true potential, the story of a weapon too dangerous for the world it was designed to protect. The true genesis of this terrifying missile, a project code named the Black Dart by Western intelligence analysts, though its actual designation remains shrouded, was not ambition, but pure, distilled Cold War fear. It was conceived during a particularly acute, terrifying moment in the late 1950s and early 1960s, a period punctuated by crises like the Sputnik shock, the U-2 incident, and the Cuban Missile Crisis, when both the Soviet Politburo and the White House genuinely believed that nuclear war was not just possible, but potentially imminent. The doctrine of mutually assured destruction was in place, but that very doctrine drove both sides to seek a technological way out, a loophole, a weapon that could be launched without immediately triggering the ultimate, world-ending response. The intelligence mirage. The panic that catalyzed the project began with a series of highly sensitive, often fragmented intelligence reports filtering through from the opposing bloc. Analysts, working in subterranean bunkers illuminated by the sickly green glow of cathode ray screens, began piecing together data that suggested the enemy was moving away from the conventional, high-altitude ICBM. The new threat, the reports whispered, was a class of weapons designed not to soar into the vacuum of space, but to hug the very atmosphere, high-speed, low-altitude weapons. The strategic nightmare was immediate and absolute. These proposed missiles, whether they were truly being built or were simply figments of paranoid speculation, represented a triple threat to the existing defensive architecture. Too fast for existing air defenses. Traveling at speeds that would make the fastest fighter jets of the era seem stationary, the missile would outpace the reaction time of surface-to-air missile batteries and ground-based interceptors. The time from detection to impact would be measured in minutes, offering no meaningful window for defense. Too low for early radar systems. The long-range radar networks of the time, the SAGE systems in the West and their counterparts in the East, were designed to scan the high upper atmosphere for incoming bombers and ICBMs emerging from space. The curvature of the Earth effectively created a blind spot, a vast, low-altitude envelope beneath the radar horizon. By flying at treetop level, this new weapon would exploit that blind spot, rendering vast, expensive early warning systems useless. Too powerful to be intercepted once launched. If the missile succeeded in evading early detection, there was simply no established technology capable of intercepting a Mach 3+ object skimming the terrain. It would be a foregone conclusion. The psychological impact of this theoretical threat was immense. The very idea undermined the expensive, complex safety blanket of continental air defense. If the enemy could simply fly under the fence, all the years of development, all the billions spent on radar installations and alert fighters, would be worthless. The technological counterpunch. To counter this existential dread, a threat that Western intelligence code-named the Soviet Hedge, and the Soviets themselves referred to as the American Shadow, engineers, both East and West, were tasked with designing a missile unlike anything built before. The logic was terrifyingly simple. If the enemy has a ghost weapon, we must build a better one. The mandate for the new missile system was uncompromising. It had to fly faster than Mach 3 over 2,300 miles per hour to ensure it would pass through any defensive zone before an alarm could be properly processed. It had to skim just above the ground, maintaining an altitude of mere dozens or hundreds of feet, to effectively use the Earth's curvature as its shield, thereby evading early warning systems. And finally, it had to deliver a warhead capable of devastating an entire city. This was not a tactical weapon, it was a strategic terror weapon, designed to destroy centers of population or command and control structures with surgical, unstoppable precision. The resultant concept alone was enough to alarm NATO and the USSR alike, because it represented the ultimate offensive weapon. Whichever side successfully deployed this missile first would gain a massive, if fleeting, advantage, a window of opportunity to strike that the other side could not reliably defend against. It transformed the strategic landscape from a mutually terrifying stalemate into a desperate technological arms race for the capability to deliver the first, decisive blow. The terrifying lethality of this missile, the element that truly set it apart from its contemporaries, was not derived from the size of its nuclear payload, but from the elegant, yet fundamentally unmanageable, technology behind it. This wasn't just a bigger or faster rocket. It was a complex system that forced materials and physics to operate at their absolute breaking points. The hybrid engine, a fusion of fire. The main challenge in achieving sustained, low-altitude, high-speed flight was propulsion. Conventional rockets carry both fuel and oxidizer, which adds tremendous weight and limits duration. Standard jet engines, while efficient, lose power dramatically above Mach 2.5 because the air intake compression becomes inefficient. The solution chosen by the missile's designers was a radical new propulsion system, a technological compromise that pushed the very limits of aerospace engineering, a hybrid engine combining a rocket booster and a ramjet. Shutterstock. The rocket phase initial boost, the missile would be launched vertically, using traditional solid or liquid fuel rockets. This was necessary to get the massive projectile up to approximately Mach 2, the minimum speed required for the ramjet to function. The sheer G-forces generated during this boost phase were enough to crush most conventional payloads. The ramjet phase sustained velocity. Once Mach 2 was achieved, the rocket boosters would be jettisoned, and the ramjet would ignite. A ramjet has no moving parts. It relies on the forward motion of the missile to ram air into the combustion chamber, compressing it before injection with fuel. This elegant simplicity allows it to operate with devastating efficiency at extreme speeds. This combination allowed the missile to accelerate far beyond the capabilities of any contemporary aircraft, achieving sustained velocities above Mach 3, potentially nearing Mach 4. The physics of failure. This speed came with a catastrophic trade-off: aerodynamic heating. When an object flies through the atmosphere at such high Mach numbers, the friction and compression of the air molecules create extreme thermal energy. The temperature of the missile's skin would rapidly climb, eventually causing the titanium and specialized steel alloys to burn hotter than its own casing could withstand. The engineers were essentially asking the metal to momentarily hold together at temperatures that threatened to melt it, necessitating exotic, difficult-to-manufacture materials and ablation coatings that often failed in testing. The weapon was a spectacular, self-destructive flare in the sky. Terrain following guidance. Flying blind, seeing everything. To realize the operational necessity of flying low, beneath the radar horizon, the missile required an equally ambitious and barely understood guidance system: terrain following radar (TFR). In the 1960s, this concept was decades ahead of its time. The TFR system utilized a small, forward-facing radar antenna that constantly scanned the topography immediately ahead of the missile. A dedicated onboard computer, a fragile assembly of vacuum tubes and early transistors, would instantly process this topographical data and send immediate pitch commands to the missile's flight control surfaces. This complex feedback loop was intended to allow the missile to literally hug the Earth, climbing over hills and plunging into valleys to maintain a predetermined, ultra-low altitude, thereby avoiding detection. The technology of instability. The complexity of the TFR system was its greatest weakness. The combination of its extreme speed and the necessity for minute-by-minute corrections made the system intensely unstable. The computer had to calculate and act in milliseconds. Even small errors, a minor fault in the radar return, an instantaneous fluctuation in air density, or a delay in the hydraulic response to the control command, could have cataclysmic effects. A slight overcorrection in a valley could send the missile plummeting into the ground. A moment's delay over a crest could send it veering wildly off course, or worse, trigger a complete and unrecoverable loss of control due to the unstable aerodynamics of the airframe. The design was a technological marvel, yet it was balanced precariously on the very edge of controllability. The missile was a testament to the reckless brilliance of Cold War engineering. It was a vehicle that pushed metallurgy to its thermal limit and computing to its speed limit, all in the desperate hope of achieving strategic invulnerability. But in doing so, it created a weapon so fundamentally volatile that its own creators had to confront the terrible possibility that they had built a device so sensitive and so powerful that it could just as easily annihilate its intended target as it could lose control entirely and become an unprecedented disaster for its own side. The shroud of secrecy that enveloped the Black Dart program, or its Soviet equivalent, depending on which side of the Iron Curtain we place its genesis, was one of the thickest ever devised. Yet, in the high-stakes, cat-and-mouse game of Cold War espionage, even the thickest fog can be momentarily penetrated by a flash of critical intelligence. The discovery, or even the solid rumor, of this missile's existence by the opposing superpower triggered an immediate, visceral reaction that rippled through the most secure military compounds: panic. The intelligence windfall. For NATO, the confirmation that the Soviets were pursuing a Mach 3+ low-altitude cruise missile, a platform capable of delivering a warhead under the radar horizon, was likely delivered by a deep penetration spy, perhaps a disgruntled scientist or an agent within the Soviet research and development complex. Conversely, for the Soviets, evidence of a similar, highly advanced, terrain-following missile in the West might have come from the analysis of exotic materials smuggled out of a test facility or from the telltale signatures of a disastrous, failed flight test detected by their global electronic surveillance network. Regardless of the source, when the detailed specifications, the combination of hybrid ramjet propulsion and terrain-following guidance (TFR) landed on the desks of the Pentagon's Joint Chiefs of Staff or the USSR's General Staff. The reaction was immediate and unified, a massive, top-priority alert. Emergency studies. The unsettling answer. Both NATO and the USSR immediately launched emergency defensive studies under the highest classification. These war-gaming exercises were not conducted in abstract. They used real-world parameters, modeling the missile's projected speed of Mach 3.5, its operational ceiling of 100 to 300 feet, and its maneuverable flight path. The question was simple, terrifying, and urgent. Could their existing, multi-billion-dollar air defense networks reliably stop such a weapon? The results were chillingly consistent across both blocs, rendering the analysts' handwriting shaky and their conclusions absolute. They couldn't. The core of the problem lay in the synergy of the missile's deadly attributes. Low altitude, zero warning. The missile flew too low. At its operational altitude, the Earth's curvature rendered conventional ground-based radars virtually blind. By the time a high-speed target popped up over the radar horizon, the defense system would have mere seconds, perhaps 60 to 90 seconds, to acquire, identify, track, and fire an interceptor. This was an impossible timeframe for the slower, first-generation surface-to-air missile systems of the era, which often required several minutes of preparation and tracking. Too fast, too far ahead. The speed of the missile, easily exceeding 3,000 feet per second, meant that the kinetic energy and destructive forces involved were astronomical. Any attempt at interception would require a missile capable of a proportional velocity and a guidance system sensitive enough to track a target flying low and fast through ground clutter. The physics were simply too demanding, too unpredictably maneuverable. Unlike the predictable, fixed parabola of an ICBM, the Black Dart's TFR system allowed it to subtly, or even sharply, shift its path to follow topographical features. This eliminated the possibility of calculating a reliable interception point. The maneuverability meant it could defeat the last-ditch defense layer. The stark reality was that the successful deployment of this single-weapon system could render entire defense networks obsolete overnight. The elaborate, interconnected radar sites, the heavily protected missile silos, the continuous alert flights of interceptor aircraft, all would become little more than expensive historical monuments, irrelevant to a war fought at treetop level. The looming arms race. This technological vulnerability created a profound destabilization in the strategic balance. For years, the stability of the Cold War rested on the certainty of the certainty that both sides possessed the retaliatory capability to survive a first strike and destroy the aggressor. The Black Dart threatened to introduce a moment of certainty of first strike, offering the aggressor a realistic chance to severely cripple the enemy's retaliatory power before they could respond. The fear was palpable. Both sides feared that the other might deploy a similar system first. If one superpower gained the ability to guarantee a strike while defending against retaliation, the incentive to initiate conflict in a moment of crisis would surge dramatically. This led to the terrifying prospect of a destabilizing arms race neither could control. It would force both nations to divert untold billions from conventional forces and social programs into an emergency program to develop their own Black Dart equivalent, or, even more desperately, into a whole new generation of exotic, space-based or high-energy beam defenses that were only theoretical concepts at the time. The pressure to match the enemy's terrifying new capability drove military planners to the edge of breakdown, forcing them to contemplate budgets and risk profiles previously deemed unthinkable. In a conflict dominated by political maneuver and grand strategy, the ultimate irony of the Black Dart missile program was that its downfall was not orchestrated by diplomacy, disarmament treaties, or the infiltration of enemy spies. The missile was not defeated by external forces, it was destroyed by its own, self-inflicted technological hubris. The project imploded from within, succumbing to the unforgiving laws of physics and the sheer impossibility of its own engineering demands. The perils of perfection. The engineers had asked the missile to achieve a degree of speed, control, and endurance that exceeded the material and computing capabilities of the era. The result was a weapon system that was simply too dangerous to operate safely, a volatile blend of raw power and structural fragility. Guidance errors and the wild goose. The complex, experimental terrain-following radar (TFR) system was the most consistent source of failure. The onboard computer, running on early-generation microchips or temperamental magnetic core memory, struggled to process the immense amount of data generated by the high-speed radar scan in real time. In testing, this led to critical guidance errors where the missile, instead of hugging the terrain, would suffer a catastrophic calculation failure. These errors caused test flights to wander wildly off course, flying hundreds of miles away from the designated range or, worse, suddenly pitching down and destroying themselves in uncontrolled dives. One instance, whispered about in closed-door briefings, involved a prototype that went completely rogue, breaching restricted airspace and requiring emergency scuttling procedures, a terrifying dress rehearsal for losing control of an armed nuclear device. Supersonic stress and structural integrity. The intense, prolonged flight at Mach 3+ generated powerful supersonic shockwaves that hammered the missile's structure. The extreme vibration, combined with the forces of high-speed turns executed by the TFR system, proved too much for the lightweight, heat-resistant alloy casings. Test footage frequently showed evidence of localized structural damage, bent fins, cracked weld points, and aerodynamic panels peeling away, even during flights that were deemed successful until the final moments. The airframe was being stressed to the point of catastrophic failure just by performing its basic mission profile. The overheating calamity, the inherent conflict between the ramjet's immense power and the limits of materials science proved insurmountable. The issue of overheating was chronic. While exotic materials like titanium and nickel alloys were used, the skin temperatures reached such extraordinary peaks that not only did they threaten the structural integrity of the outer shell, but they also severely jeopardized the sensitive internal components. Avionics, hydraulic fluid, electrical wiring, and, most critically, the nuclear warhead's delicate safety and arming mechanisms, were all subjected to temperatures that threatened to melt components mid-flight. A missile that melts down before reaching its target is merely an expensive dud. One that melts its safety mechanisms is an uncontrolled nuclear disaster. The ultimate risk assessment. The engineers and military leaders who oversaw the program were forced to confront a brutal truth. The missile's technological demands made it fundamentally unreliable. The risk of the weapon failing to deliver its warhead was high, but the risk of the weapon failing catastrophically, falling onto a friendly nation or, potentially, suffering a thermal runaway that compromised the warhead's safety features, was unacceptably higher. One internal program review, delivered to the highest command authority, laid out the dilemma in stark, unforgiving terms. It was a report that killed the project more effectively than any defense system ever could. Deploying this weapon in combat conditions is equivalent to accepting a high probability of losing control of a nuclear device within our own operational theater or that of an allied nation. The failure rate is not a technical problem to be solved with more funding. It is a fundamental flaw of this technology at the current level of scientific understanding. No rational commander, East or West, was prepared to sign off on that risk. The potential for an accidental nuclear catastrophe caused by an errant, superheated missile, a disaster known internally as a broken arrow event, was too great a liability, far outweighing the perceived strategic gain. The Black Dart was a weapon that terrified its enemy, but it terrified its own creators more. The inevitable decision was made. The program was quietly, systematically halted. The vast test facilities were mothballed, the prototype missiles were scrapped, and the surviving engineers were reassigned to less sensitive, more conventional projects. The missile that promised to win the Cold War by sheer speed and unpredictability never entered active service. Its genius was its downfall, proving that even in the ultimate technological arms race, the ultimate cost of perfection is often practical impossibility. The official termination of the Black Dart, or its equivalent, was handled with the same extreme secrecy that governed its genesis. The cessation of funding, the dismantling of the prototype launchers, and the reassignment of the top-tier engineering talent were all conducted under the highest possible security clearance. This was not a project that was allowed to fail publicly. It was too sensitive, too revelatory of the vulnerabilities inherent in the pursuit of absolute supremacy. The military and political leadership on both sides understood that the very existence of such a concept, a weapon too hot, too fast, and too temperamental to use, was, in itself, a strategic liability. The process that followed was the bureaucracy of oblivion, a systematic effort to erase the program not just from the public eye, but from the official historical record itself. The shelving and the scrutiny. Most of the documents surrounding the project were quietly shelved. They were not simply thrown into a basement. They were carefully filtered, segregated, and dispersed. The initial internal reports detailing the technical failures, the high probability of guidance errors, the rampant supersonic shockwave damage, the fatal thermal instability, were sealed under classification levels that far exceeded the standard top secret. They were often marked with multiple, overlapping special access programs, SAPs, or compartmentalized control systems, CCS, ensuring that only a handful of individuals in the highest echelons of power could ever request and authorize their viewing. The materials were scattered across different agencies. Propulsion reports went to one vault, guidance computer data went to another, and the truly catastrophic thermal test results were stored in a third. This act of dispersal, of preventing any single archive from holding the complete, reconstructible narrative, was a conscious effort to ensure that the idea itself could not be easily resurrected by a future, perhaps less cautious, administration or generation of generals. Some were classified for decades. Decades later, historians and curious defense researchers began poring over the declassified records of the 1950s and 60s. They would occasionally encounter tantalizing fragments. A cryptic requisition order for high-temperature ablation materials, a brief mention of a MACH-40FR project failure, or a photograph of an unusually shaped ramjet nozzle. But the crucial narrative links, the binding explanations, and the names of the principals remained locked away, sometimes requiring presidential or Politburo approval for release. The veil of secrecy remained intact, transforming the missile from a technological failure into an enduring myth. Others simply disappeared. In the chaotic handovers of power, the retirements of key personnel, or the deliberate shredding of sensitive papers following national crises, certain core documents vanished entirely. They may have been misfiled, destroyed by error, or quietly removed by senior officials who believed the world was safer if the details of this particular madness were never seen again. These were the most dangerous records, those that outlined the precise mechanism by which the nuclear safety systems could have been compromised by the thermal instability of the ramjet casing. The cautionary tale in the war room. The missile never became a physical fixture of the global conflict, but its memory remained a powerful, invisible force in strategic planning. The missile became a cautionary tale taught to every new generation of strategists and engineers on both sides, a reminder that technological ambition, when pursued with ideological fervor and divorced from the cold realities of physics and material science, can push beyond the limits of what nations are prepared to unleash. The lesson was profoundly simple. Reliability is the ultimate deterrent. An ICBM that can be tracked, but is guaranteed to hit its target, is strategically superior to a weapon that is theoretically unstoppable but has a 40% chance of incinerating a city hundreds of miles off course, or worse, exploding on its own launchpad. The Black Dart failure shifted the engineering focus from achieving impossible speed to ensuring verifiable, robust precision. It taught the world's most powerful militaries that the race for supremacy had to be fought within the constraints of established, controllable technology. This project, which failed to achieve combat readiness, arguably did more to shape later arms control talks, which focused heavily on verification and stability, than many of the systems that actually became operational. The uncontrollable edge, it never reached the front line. It never flew in combat. Its story remains a shadow history of the Cold War, a brief, sharp moment when the pursuit of an overwhelming advantage was suddenly checked by an internal realization of existential risk. The truly terrifying part of its legacy was not the potential destruction it represented, but the lack of control. The world learned to live with the fear of the deployed ICBMs, weapons that were terrifyingly fast, but predictable, weapons that allowed for verification through satellite monitoring and whose trajectories were mathematically precise. This predictability, however awful, allowed for the fragile framework of MAD to function. But for a brief, panic-stricken moment in history, this unnamed missile terrified both NATO and the USSR more than any deployed weapon, because it proved that the race for supremacy could easily cross into the realm of the uncontrollable. It introduced a scenario where the ultimate weapon could turn rogue, where the ultimate power was wielded not by the generals in their bunkers, but by the unpredictable, unstable forces of engineering failure. That brief vision, of a hypersonic nuclear device streaking across the continent, no longer obedient to the commands of its creators, its fate determined by a microscopic flaw in a computer chip or a stress fracture in a piece of exotic metal, was enough. It was a self-inflicted wound to the pride of both superpowers, a silent admission that in the quest for the ultimate weapon, they had built something too reckless, too flawed, and ultimately, too human to be trusted with the fate of the world. And so, The world simply forgot it, burying the terrifying lesson under layers of silence, hoping never to have to remember the missile that promised total victory but guaranteed only chaos.